So my name is Land-Strykowski, and we've heard a lot here about really interesting things, about the S8 tension and the Hubble tension, and now I'm going to shed some light on another tension that you might not know about. If you haven't heard about the cosmic dipole anomaly before, that's okay. By the end of this talk, you have an understanding of what the problem is, why it is interesting, and what we are doing about it. This stems from the cosmological principle, a very big assumption in the way in which we view the universe. It's the idea that statistically, the universe should be homogeneous and isotropic on large enough scales. This assumption is really important. It makes up, it's part of the derivation of the Freeman-Lemaitre-Robertson-Walker metric. And that assumes isotropic expansion of the universe. And then that is also involved in our standard concordance model of cosmology, lambda CDM. So if the cosmological principle was to break, then all of these stones that are stacked on top of it would come tumbling to the ground. That's our lambda CDM. So if the cosmological principle is so important, then it is also essential to constantly reinterrogate it, and therefore reinterrogate the evidence that supports it. And one of the biggest pieces of evidence for that is the cosmic microwave background, this radiation from the very early universe where it looks pretty smooth. These temperature fluctuations are of order delta T on T 10 to the negative 5. So it's essentially the same temperature everywhere. The idea is that if these small temperature fluctuations then grew via gravitational instability over cosmic time to give us the large-scale structure in the universe, then the smoothness here should be imprinted on matter. We should find cosmologically distant sources to also be homogeneous and isotropic. But this isn't actually the CMB. This is what it really looks like. It has a big anisotropy, a big temperature dipole. And this is typically interpreted as being an effect of our motion, because we are not co-moving observers with the cosmic rest frame. Our heliocentric motion, our peculiar velocity, causes this shift, where the temperature is shifted at the poles towards a certain location in galactic coordinates at around 370 kilometers per second. And that is totally fine. But if this imprint, if this temperature dipole is caused by our motion, we should see this same imprint on other sources in the universe that should be distributed homogeneously and isotropically, such as sources that are very far away. What our motion would do when we're observing sources on the sky is cause a relativistic aberration, where if you're stationary and you have an object at a certain angle towards you, that angle will shift when you start moving. It will become tighter in the direction of motion. If you're doing this for lots of sources at the same time, for example, in a large catalogue of objects, it's a little bit different. Here you would have divvied the sky up into equal area pixels. That's what the different colors of these squares are. And I've put the same number of sources in every pixel, and we're just focusing on the center ones there. We've got 4 sources in each pixel because everything is homogeneous statistically. Then I want us to imagine that we are now moving towards that center pixel on the sky. Your motion will cause relativistic aberration, causing all those to move closer and closer together. This means that the source density of objects that you measure per pixel will increase in the direction of your motion, and it will decrease in the direction that you're coming from. Your motion will also cause a Doppler shift. Here, when you're talking about objects in a catalog, you always have flux density limits, an upper limit, but most importantly, a lower limit in your survey. Objects below this, you're not counting. Maybe they're too faint, too spurious, too close to the completion limits of your survey, so you don't include them. But because objects in the direction of motion will be blue shifted, you'll see their frequency increase and their flux density also increase. This means you'll detect more objects in front of you because objects that shouldn't be in your survey will get boosted in. In the anti-direction when you're coming from, objects will then get boosted out, meaning that if you put all these effects together, the aberration and the Doppler shift, you detect more objects in front of you that are closely packed. So you can see how the source density of objects changes on the sky. And in an equation form that was first proposed by Ellis and Baldwin in 1984, you get this beautiful relationship. You get aberration and Doppler shift working harmoniously right there. And if you plug in reasonable values of x and alpha in your velocity, you get that this dipole modulation across the sky is a really small effect, around a 0.1% modulation. So hypothetically, if you had equal area pixels in the sky and about 1,000 sources in every pixel, then with a dipole amplitude of 0.1%, you expect at the poles, where this effect is the strongest, to get plus or minus 1 source. So we've set ourselves up with a very difficult problem and a small thing to measure. So, over the last 40 years, just to recap to cosmology, because we've talked about dipoles a lot, what we can do is we can take a catalogue of objects on the sky and see how the source density changes. From there, you can infer an anisotropy, a dipole. You can place some of that as being a kinematic effect, but any deviation from that must be something else. Lambda CDM does predict clustering on small scales, but then that would only throw off the dipole by a certain amount. Any excess of a difference from the expectation from the CMB tells you that something else is happening. There's some kind of anisotropy, some weird thing going on in the distribution of your sources, and that would inherently disagree with the cosmological principle. So that's how the dipole links here to cosmology. So people have done this test over the last 40 years, and they've found that the dipole directions pretty much agree with the CMB. You can see the star here, which is the CMB location, and these contours of large radio surveys, which I'll cover in more depth soon. And we see it's in the right quadrant on the sky, and we have agreement. But then the amplitude is a different story. That consistently exceeds the expectation from the CMB. Ideally, we'd have everything line up with that gray vertical line at 1 times the CMB amplitude. But instead, at infrared, optical, and radio continuum, we find that the amplitude is consistently 2 to 3 times the expectation. If you're assuming this is a kinematic effect, this means we're not moving at 370 kilometers per second. We're instead moving at, what, 800, 900, 1,000 kilometers per second? And that is in clear disagreement with other sources. And this problem is getting worse. Over the last 40 years, as people have done this test, initially we thought there wasn't a big issue. But as we've got larger and larger radio surveys and more statistical techniques to probe this, we've found a larger tension. You can see there's a lot of citations to this problem in recent time. We are working on it a lot. And now it poses a serious challenge to the standard cosmological model and the cosmological principle. And this is now comparable to the levels of the Hubble tension. We're talking about sigmas. But it's also more fundamental than Hubble. When we talk about H0, that's a problem of something inside our universe model. But the cosmic dipole is telling us that that universe model might be built incorrectly itself. Maybe it isn't Friedmann, and maybe we have to break isotropy. When we talk about tension, there are 3 main pillars. You can quantify it by getting posteriors, running your nested sampling on a data set, and looking at how those posteriors compare to known expectations. For example, the CMB measurement. So that's parameter estimation giving you parameter tension. But then you can also get tension between models. Let me fit a model where I can put the dipole at any point on the sky and see how probable my data is given that model, my evidence. I can then compute the same thing for a different model. Let's say I put the dipole parameters fixed on the CMB expectation. I get another Bayesian evidence, and you take a ratio to get a Bayes factor. And both of these have been done for the cosmic dipole problem, but people haven't looked at the tension between data sets themselves. Bayesian tension quantification. This relates to what Dilly talked about in her talk yesterday, where you have an underlying model, and you're seeing, do different data sets make the same predictions on that model? And here, also relating to Dilly's talk, we have the R statistic. You can convert this to a sigma level of tension. And what this R ratio is telling you is the likelihood, the Bayesian evidence of observing your data when they're both in the same room together, A and B. And you compare that to the likelihood of observing your data when you've got A by itself and then when you've got B by itself. So if this is much greater than 1, you're seeing when your data sets are in the same room, your confidence in both of them increases. If R is much less than 1, you're saying when your data sets are in the same room, you're less confident in either of them. You'd much rather see them separately. You'd much rather prefer that they're different parameters on an underlying model and different physical phenomena. And that's why this can reveal tension. So the surveys that we look at are the ones I mentioned earlier. The NRAO VLA Sky Survey, observed at 1.4 gigahertz around 20 years ago. This is a Northern Hemisphere ground-based survey. And we also compare this to the Rapid ASKAP Continuum Survey done around 2018-2019. These are the RACS 1 observations at 887.5 megahertz. We not only compare these to each other, but we also compare these to infrared-selected quasars from the WISE satellite catalogue. Here we use a certain color cut used in the literature to filter out objects that we don't want to look at that are not at cosmological distances. For example, stars which can emit in the infrared. And this is observed at the W1 and W2 bands. And then we also compare these to observations of the CMB, Planck. The reason we're running our machinery again on Planck is because we need to get the Bayesian evidence for the tension quantification. And we want to treat all these data sets the same way. And when we're running our analysis, we test it for the different observational frequencies of the CMB. We also use different component separation algorithms to remove the foreground galaxy component. And we also test just masking that out, like we've masked out the galactic plane in the other surveys. And we find that treating Planck in these different ways has no significant effect, as long as you remove the foreground galaxy in some way. These observations, other than Planck, the other surveys, they've been smoothed, boxcar smoothing within 1 steradian, so that we as humans can see the large-scale structure. And we can instantly see that we're going to get tension. We're going to get problems comparing these to Planck. Planck, we have a very strong dipole. RACS, there's a lot of vertical structure. And in NVSS, if you blow your eyes, you can see a dipole, but there's definitely higher level structure there. And in CatWISE, you have a dipole, and you have a quadrupole as well. So instantly, we're going to get some tension. And before we move on, it's important to note that we have different levels of information that we're working with. The radio surveys, NVSS has around 350,000 sources, RACS has around 450,000, and the CatWISE sample that I'm using has 1.6 million. So we're expecting to get different constrained posteriors based on these information levels. So what's the tension? Well, here we have the nodes of our 4 datasets, and we'll start by looking at Planck and CatWISE. We find 5 sigma tension with Planck. This corroborates the recent results in literature, also looking at CatWISE, that find a similar result, and this corroborates the challenge against the standard model of cosmology. But the radio surveys are a little bit of a different story. They're in moderate levels of tension with Planck, and the reason for this, whilst they're centered at different places in the posterior space, is that these are larger, unconstrained posteriors due to the lower level of information. So we have moderate tension only. What is very interesting is that CatWISE and NVSS are in essentially no tension. This is very strong concordance at only 0.5 sigma tension. These 2 datasets have posteriors in the parameter space right on top of each other. And this is telling us that systematic effects causing this tension are disfavored. CatWISE and NVSS have completely different systematics. One is a ground-based survey, one is a satellite. They're about 20 years apart and in different continuum. So this is telling us that there is favor for there being a physical phenomena underneath the tensions that we observe, a source dipole of the same source. RACS, however, is a different story. It appears to be in moderate tension with all of the other surveys. This suggests that there might be some unknown, subtle systematic effect in the catalogue itself or the underlying observational data. And the reason I say subtle is because RACS is fine, but we're trying to test, remember, a 0.1% effect modulation across the sky. So any small deviation, for example, from ionospheric temperature fluctuations and the inherent flux scaling that we do to compensate, can cause the dipole to be different. Here, just again, qualitatively, if you look at these different RACS catalogues, which are at different frequencies and have been scaled or not scaled, you can see there's very different large-scale structure, and therefore you'd infer a different dipole. These are preliminary results, but it tells us that the future is going to be modeling and understanding systematics to the bone. Moving on, we start to use simulations. Because those radio surveys are at only a moderate level of tension, what if they had more information? What if those posteriors are really tight? When can we expect to get that golden 5 sigma tension measurement that that golden 5 sigma tension measurement that we come to understand as being a point of detection? So, we start with a homogeneous sky, the same number of sources in every pixel. And then we input a dipole and change the modulation to get an expectation value in every pixel. And because this is counting statistics, it is a Poisson point process, we then take Poisson counts to infer noise into our data set. And we do this for 50,000 or up to 50 million sources at 31 different intervals, logarithmically spaced. What this translates to is about 20,000 nested sampling runs. So it's a bit expensive. And we do it with different dipoles as well. We put in an NVSS or RACS dipole representing the radio continuum, and we also put in, as a control, simulations of the Planck dipole. All these dipoles are the best fit medium parameters from our nested sampling searches earlier. And we compare these with the Planck data itself. So here, comparing Planck dipole with Planck data, we don't expect to see tension. This is our control, this is the CMB dipole. But for a radio continuum dipole that is in disagreement with Planck, we expect to see tension, especially when we have a high level of information. So the results are the following. We're going to break this down. We have different slices of the number of sources that we're using for the information, and on the x-axis, this is the tension that we measure with the real Planck data to the observations, to the simulations. What we find is where we have the smallest level of information, the blue and red distributions are right on top of each other. This is telling you that if you're measuring tension around the 1.5 or 2 sigma level, you can't tell whether your data is a by-chance concordance data that was statistically different, or if it is a real tension that's happening. You can't tell. The posteriors are too unconstrained. We're seeing the effect of shot noise here, where the signal-to-noise ratio is really low. Now, whilst that's an extreme hypothetical, moving towards the middle paddle, which is about the number of sources that we're using in our real radio surveys, we also have unclear inference. In the middle there, at around 2 sigma, which is the tension that we measure in our radio surveys, we get degeneracy, where again, you can't tell whether it's concordance or tension that you're seeing. And what we'd really like is in the future, where we have a lot more sources. In the future, we'll see something more like this. The two distributions are very far away. Therefore, if you have concordance, you'll see very strong concordance, because it's right on top of the Planck location. If you have tension, it'll be very far away, very constrained type posterior. You'll get those measurements straight away. And looking towards the future, we're on the cusp of doing this. If you assume the NVSS centered location in parameter space for the dipole, you can get a 5 sigma measurement of only around 1.3 million sources. If you assume the same thing for RACS, that's 1.5 million. And in the context of large surveys coming up, such as SKA, we're going to have a plethora of data, and we're on the cusp of untangling this anomaly. So what this means for the future, if this dipole tension is a real thing, is that we need to wind back the clock and think about our large cosmological view. Maybe homogeneity and isotropy is not the answer. There are solutions to the cosmic dipole problem where you could get an inhomogeneous cosmology. You could have a large dark matter void, about 1 to 3.4 gigaparsecs, and put an observer in the middle. You off-put them by a couple of hundred megaparsecs, and that could account for these strange observations that we're seeing in these large data sets. And that would obviously break the cosmological principle. But you can also do anisotropic cosmologies that are not Friedmann, where the universe evolves in a certain direction, which could account for clustering that we see in these data sets as well. Or it could also be something completely new. But again, to recap what I went through today, the cosmic dipole tension appears to be one of the most significant tensions, or at least the most fundamental, and it's time to probe that even more. And the CatWISE results corroborate recent literature, where we have an over 5 sigma tension that challenges our standard concordance model. And NVSS and CatWISE being in close proximity to each other and high concordance tells us that there may be a source dipole there, that it's not just systematic effects causing tension, which is really exciting. And RACS requires further investigation, telling us about what's going on. These small temperature fluctuations could be throwing off the dipole, and it's time to probe that and model that using cutting-edge Bayesian statistics. And then, in the future, LSST, SKA, Euclid, Sphere X, Roman, all these data sets are a plethora of sources. And if we can understand these systematics really well and model this sensitive dipole to the T, we can work out what is going on in the universe. So, thank you very much for listening. All of the content of this talk has been put together into a paper and submitted to monthly notices of the Royal Astronomical Society. Feel free to look at it on the website when it is uploaded, or look at previous talks on this content in closer detail. But other than that, I will open the floor to questions. Thank you.
Thank you very much. Questions, please. Yes?
Thank you for a very interesting talk. Yeah, so I have a couple of questions, actually. I guess the first one would be, so this discrepancy that you see with the RACS dataset and the other datasets, could that be assuming that the dipoles that you are measuring are cosmological dipoles? I mean, could there be a non-kinematic interpretation
yes,
that would explain why you would actually not see the same Ellis-Baldwin dipole?
Yes. So, just to check I understand the question fully, that with the different dipoles that we see in NVSS and RACS that are in the same continuum, is there an explanation for that that's not kinematic? Is that the question?
Yeah.
Fantastic. So, whilst these are the same radio continuum, they are at different frequencies. And because of the relation that we have, we'll go very fast back to it. Yes. because of the relation that we have here, we expect to get a different dipole amplitude, because x and alpha are based on the objects that you're looking at and that relation between the source counts and the flux density. So you expect to get a different amplitude. But that doesn't explain the difference in direction. So in terms of the different large-scale structure we see in NVSS and RACS, that is a bit more questionable. And in terms of where that's coming from, that's why we're going to start probing the systematic effects deeper. Yeah.
Yeah, and regarding that, have you considered, have you looked at the size of the quadrupole, for instance, and octupole, the higher order multiples, and see, like, to get a hint of what your systematics are there?
Yes, absolutely. So my colleague Oliver Oeda has another talk in the Cosmic Dipole tomorrow, and he'll talk about some things that he's done looking at higher order multipoles. But we do have approaches to fit quadrupoles, octupoles, and what we find is that it is strong in CatWISE. In NVSS and RACS, I'm not quite sure of that exact result. But you can see that you have a higher order vertical structure in RACS. But in terms of higher order multipoles, I do not know how strong they are. I haven't done that test, but I don't think they'll be anywhere near as strong as the dipole. But thank you.
Thank you.
Next question.
Hi, Marley. Great talk. Doesn't the structure that you see in the catalogues that is not consistent with a simple dipole indicate that there is spurious clustering modes caused by the detection, variability in the source catalogues, and all of these sorts of things? And doesn't that imprint itself on the signal in a fairly significant way?
Yeah. So we're trying to detect a dipole where there's other imprints that should be there from spurious local sources. I didn't quite cover this in depth because, again, my colleague will cover it tomorrow, but we do remove local sources from NVSS, RACS, and CatWISE. We cross-match within 0.1 redshift with the NASA extragalactic database and the 2-mass redshift survey. But even then, there's still likely some spurious sources there because these redshift surveys are incomplete. And also, it is difficult to cross-match from radio to infrared optical, which is where those redshift surveys are. So indeed, there is likely local sources throwing off the dipole, but whether that can get a 5 sigma tension down to 2 is an unsolved problem. I think the general consensus is that even with local sources, it can't explain the very vast dipoles that we're seeing here, even with that.
Okay, thanks.
Yes.
Very interesting talk. So I'd like to ask about errors. So I understand that now we have mainly constraint related with number of objects, right, in catalogs. But what about redshift distributions of these objects? For radio sources, we know that they aren't well estimated. So what fraction of errors comes from
that's a really good question of what redshift are these sources that we're looking at. I'll just bring up the slide of the surveys themselves. That's nice. The redshift distribution has been estimated for CatWISE using the highly complete stripe 82 region of SDSS that was done by other people in the literature. And they find that the CatWISE quasars, and I guess this is the most important result to talk about because this is the highest tension with Planck, the CatWISE quasars are all at moderate tension. Only 1% is less than 0.1 redshift. And even of that 1%, majority of them will be very close to 0.1 redshift. So they're all at moderate. They're all at the point where we don't expect to get scaled structure at the scale that we're seeing here at these redshifts. Does that answer your question?
Yeah.
Hi, Mali. Thanks for the very nice talk. I have a couple of questions. In your analysis, I am assuming, I don't know, have you taken into account the exposure time of the different surveys and also the Malmquist bias into account?
Yes. In terms of exposure time,
yes.
I'm very much not sure. I'm not as much on the observational side, and that instantly I find compelling, and I want to look at papers into that immediately after this talk. In terms of the Malmquist bias, or the Malmquist limit, that was something brought up by the referee in our recent report that we're chatting about. But even then, based on looking into it, it can't account for all the tension that we're observing.
Okay, I think that the exposure time, it's very worth checking out, especially given that you're using number counts to measure the dipole.
Fantastic. I'll mention that to our collaborators, because I'm working with the CSIRO who run the RACS surveys to understand all the things there. But I'd assume if there's something like that would be so fundamental throwing this off, I would presume people would have accounted that at the catalogue level when they're calculating the number of sources. But even then, I'm not sure. I'll chat to you more about this. That sounds great.
We can talk later.
Thank you. Yeah.